Hi friends and my dear students, a very warm welcome to all of you for my session today. Today we are going to learn something very important from the exam point of view. That is calculation of number of atoms in a unit cell. In fact friends, so many questions have been asked frequently from this topic in both the board exams as well as the different types of competitive exams. So please pay more attention throughout this topic, okay? Okay friends, before we learn how to calculate the number of particles per unit cell, let us first try to understand the contribution made by each and every constant particle to a particular unit cell. Okay, for that, take a look at this crystal lattice. Can you see here? There's so many unit cells present in all the three dimensions, and each unit cell is surrounded by many such neighboring unit cells. And all the adjacently placed unit cells are in fact touching each other, isn't it? Therefore, we can't possibly remove one unit cell out of the crystal lattice, right? And guys, we also know that every lattice point is occupied by one constant particle, right? So, look at this constant particle at that particular lattice point. This is actually shared by many such neighboring unit cells, right? That means this particular constant particle does not belong completely to one particular unit cell. Instead, only a small portion of it or a fraction of it in fact belongs to that particular unit cell. In other words, guys, this constant particle at a particular lattice point is actually contributing a part of it to one particular unit cell because it is shared by so many neighboring unit cells as we can see here. Therefore, let us now learn the contribution made by each and every constant particle to a particular unit cell. And do you know, the contribution made by the constant particle in turn depends on where exactly the particle is present. I mean to say the position occupied by the particle. And we know the positions occupied by particles can be either at the corners or the centers. That is, centers can be either body center or face center, isn't it? And the contribution made by these constant particles will be obviously different in different types of unit cells because in different unit cells, they occupy different positions, isn't it? So now guys, let us learn the contribution made by each and every constant particle in different types of unit cells. Okay? And to keep it simple, throughout the discussion, let us assume the particle to be atom. And hence, I actually mentioned the topic to be calculation of number of atoms per unit cell. Okay? Okay, let us see the contribution made by atoms at different positions. Fine. To begin with, let us take a corner atom. For that, take a look at this crystal lattice. Can you see that corner atom? It is shared by 8 unit cells, isn't it? Can you see there are 4 unit cells in the lower layer and 4 more in the upper layer, right? So, since this atom is shared by 8 cells, obviously, the atom does not completely belong to one unit cell, isn't it? Instead, only a portion of it or a part of it only belongs to one unit cell, right? So here, as this atom is shared by 8 cells, obviously, one cell will get a share of 1 by 8, isn't it? Therefore, my dear friends, the contribution made by such a corner atom to a particular unit cell is 1 by 8, right? Now let us see the contribution made by face-centered atom. Okay. For that, take a look at these 2 unit cells. They're adjacently placed, isn't it? And they are touching each other. Both have one common face and there is an atom sitting at the center of the common face. Can you see that? Yeah. Since this atom is shared equally by 2 unit cells touching each other, obviously, that atom does not completely belong to either of the unit cells. Instead, only a portion of it belongs to each unit cell. Okay, since this atom is shared by 2 cells, obviously, each cell will get a share of only half, isn't it? Therefore, my dear friends, the contribution made by a face-centered atom is always half. Okay. Now let us take a body-centered atom. For that, take a look at this unit cell. Can you see an atom present inside that cell? In fact, this atom is actually occupying the center of the body of the unit cell. Therefore, this atom can be called as a body-centered atom. Fine. But as you can see here, this atom is not shared by any of the neighboring unit cells, isn't it? Therefore, this atom completely belongs to that particular unit cell. Therefore, my dear friends, as the whole of the atom is belonging to one particular unit cell, obviously the contribution made by such a body-centered atom to one particular unit cell is 1. Okay? Okay friends, until now we saw how each and every atom makes its contribution to a particular unit cell depending on the position it occupies, isn't it? Just to sum up, if the atom is present at the corner position, the contribution made is 1 by 8, isn't it? But if it is present at the center of each phase, then only half of the atom belongs to one unit cell. That is, the contribution is 1 by 2. But if it is present at body center, that is, when the atom is present exclusively within a particular unit cell, and we know it's not shared by any of the neighboring unit cells, in that case, the whole atom belongs to that unit cell itself. Therefore, the contribution is 1. So, please guys, keep this in your mind so that this will help us to proceed further and, okay, calculate the number of atoms per unit cell. This is very, very important from the exam point of view also. Okay, we'll take up different types of unit cells. To begin with, let us consider primitive cubic unit cell or the simple type. And you know, yes, this is the unit cell which is representing the simple type because it has the particles, or let us call atoms throughout our discussion, right? Atoms only at the corner positions, isn't it? Therefore, there are 8 atoms at the corners, right? Now, just now we saw the contribution made by each corner atom is 1 by 8, isn't it? And how many such corner atoms are there? You can count for yourself. It's 8. 1, 2, 3, 4, 5, 6, 7, 8 are there, isn't it? Good. Therefore, what do you think is the number of corner atoms present in one unit cell? In other words, how many corner atoms belong to one unit cell specifically? Okay. To understand this, it's very simple. If each of the atoms' contribution is 1 by 8 and 8 such atoms are present, obviously, if you multiply both, you will get the number of corner atoms belonging to one unit cell per se. That means 1 by 8 into 8 is nothing but 1, isn't it? Therefore, my dear friends, please remember number of corner atoms present in one unit cell is 1. Okay. Shall we proceed now? Very good. Let's take up face-centered cubic unit cell, in short FCC, and that is a structure you know. Here we have particles both at the corners as well as at the centers of all the faces, right? Therefore, here we need to calculate the number of atoms, okay, present at the corner positions as well as at the face centers. Just now we saw the number of corner atoms per unit cell is 1, isn't it? Right. What about the number of face-centered atoms? For that, we need to consider the contribution made by each face-centered atom. That also we know, just now we saw it is half. How many such face-centered atoms are present? 6, isn't it? Yes. Look here. We have shown in green. 1, 2, 3, 4, 5, 6. So guys, yes, this is 6. Therefore, number of face-centered atoms per unit cell will be half into 6, isn't it? And that will be 3. So let us write 3 here. Therefore, now total number of atoms per FCC unit cell due to corners and face-centered positions. Okay, that will be 1 due to corner, 3 due to face center. Hence, if you sum up, it comes to 4. Please keep this in mind. Okay, very important. Let's proceed. Yes, to BCC, that is body-centered cubic unit cell. And we know here the atoms are present at the corner positions. In addition to that, we have one fellow sitting inside the body of the unit cell. I'm talking about the atom present at the body center. Correct? Yes. We know the number of corner atoms per unit cell is 1. Just now we saw that. What about the contribution made by each body-centered atom? It is 1. That also we know. Very good. How many such body-centered atoms are present within one unit cell? Only 1 possible. Therefore, the number of body-centered atoms per unit cell will be 1 into 1. The contribution is 1 and only 1 atom is present. Therefore, 1 ones are 1. Now tell me the total number of atoms, right? Due to corner position and body center. Due to corner position, just now we saw it is 1. Due to body center also it is 1. So 1 plus 1 is 2. Okay. So this is the number of atoms in one BCC unit cell. Okay, body-centered cubic unit cell. Got it? Now let's solve some problems on crystal lattice and unit cells and number of atoms in a unit cell. Okay, we have clubbed 2 topics together in the same chapter, that is solid state. So let's look at the first question now. Yeah, the number of atoms in 2.4 grams of body-centered cubic crystal with edge length 200 picometer is what? The question is number of atoms. And the data given is density and of course Avogadro number, you know that. This question is picked up from case set 2019 question paper. Right, what is the given data, my dear? Once again, quickly. Edge length means what? A, isn't it? A is given. How much is A? 200 picometer. Okay. Then what else is given? Mass is given. Okay. Mass. That is 2.4 grams. BCC means what is Z? What is Z here? Number of atoms per unit cell. In BCC it's 2. Do you remember? Just try to recall, others I'll show you once again. Okay, density is given. That is 10 gram per centimeter cube. Of course, Avogadro number we know. What's the question now? Number of atoms. N, let us say. Okay. Fine. Let's look at the solution. Okay. First of all, what is the formula? You remember for density? D is equal to, yes, molar mass or gram molecular mass, whatever you can say, into Z divided by Avogadro number into A cube into 10 power minus 30, because A is given in picometer. Therefore, you need to include this, right? You can't directly go and find out the number of atoms. First, you should find the molar mass. Therefore, the step 1 is to find M. Okay. To calculate M, just bring M here. That's it. Let's cross multiply now. So Z will come down. What is Z? 2. Yeah. What is density? These two, right? This and this entire thing you have to multiply. Then D you can put here directly. 10 into Avogadro number is given here. 6 into 10 power 23. Okay. Into A cube, that is 200 whole cube. Isn't it? Into 10 power minus 30. Okay, I think we can cancel 2 and 6. That is 3 times. Okay. Now we have, right, 200 whole cube. How can you simplify this? We can say like this, 2 cube into 100 whole cube. 100 is 10 power 2. So that will be 10 power 2 whole cube. There's nothing but 8, and this is 10 power 6. And we already have 10 power 1 right here. 10 power 23 and 10 power minus 30. Nothing in the denominator. So what is left out? Only numerator we have now. So this is 3 is also there, right? Yeah, into 3. Okay. So this 3 8 is 24 into, this is, yeah, 1 plus 6, 7. 23 plus 7, 30. Plus 30 minus 30, that is 1. Therefore, 10 power 0 it will be, that will be 1. Okay. Therefore, it is just 24 gram per mole. Okay. Once, let me write neatly for you, 24 gram per mole. That is gram molecular mass. But from gram molecular mass, how can we find the N now? This next step is N. To find N, okay, we know as per definition, 1 gram molecular mass, that is GMM, right, contains how much? Avogadro number of atoms. That means here it is 24, isn't it? Therefore, 24 grams contains Avogadro number, that is 6 into, we'll take the same thing, 10 power 23. Therefore, 2.4 grams given mass contains how much? Okay, simple. Cross multiply. 6 into 10 power 23 into 2.4 whole divided by 24. This can be cancelled, right? This will be 10 times. So if 10 goes up, it is 10 power minus 1. Therefore, it is 6 into 23 minus 1 is 22. Therefore, it's 10 power 22. This is the answer. So which is the right option now? Obviously, 6 into 10 power 22 is A, isn't it? So A is the right option. Okay. Did you understand? Shall we go to the next question now? Okay. In FCC, the unit cell is shared equally by how many unit cells? Yeah, do you remember this structure of FCC, please? Okay, let me draw. FCC is what? Face-centered cubic unit cell. Okay, so let's draw one unit cell at least. It's very simple. Draw one square and one more square like this. Then join. Simple. Okay. But in FCC, yes, where are the okay, in FCC you have atoms at corners, right? Corners like this. Okay, also at the face centers in this way, top face, bottom face, these two side faces, back face and the front face. Okay, this is one FCC unit cell, but the question is, this unit cell is shared equally by how many unit cells? How many faces are there, my dear? In any cube for that matter, there are 6 faces, isn't it? What are they? Just now I said top face, bottom, these two side faces, front and back. Right? That means there should be how many unit cells touching this around it? There should be obviously 6. 1 on top, 1 below, 2 at the sides, 1 behind and 1 at the front. Therefore, you have 6. Therefore, the right answer is 6. Okay? Option C. This question is from KSET 2018, mind you. Let's go to the next one now. In a face-centered cubic arrangement, that means it is FCC. So let's draw quickly because with the diagram you understand better. That's my opinion. Hope you also agree with me. Okay, let's draw it quickly. Right. As I just now showed, 2 squares in this way. Join them quickly. Right? Good. Okay, if this is FCC, you should have just now showed at the corners and at the face centers. Now, what are the atoms at the corners? A, look here. A atoms at the corners and B atoms at the face centers. One of the A atoms is missing. Okay, that means how many corners are there? 8, isn't it? Missing means 8 minus 1, 7. So let's draw now A atoms. So I have chosen yellow. So 1, 2, third corner, fourth, fifth, sixth, seventh. Let us say this is missing now. It's already given. One of the atoms is missing. Out of 8, 1 is missing with 7. Okay. Now, where are B? B is at the face center. Let's take one more color. Green. Okay. Face centers. Center of each face. 1, 2, 3, 4. Back 5. Front 6. Very good. Now, what is the simplest formula of this compound? Okay. Yes. It should be A is to B. We have to find their numbers. Okay, A. Now, what is the contribution made by the corner atom? We know it's 1 by 8. But how many such corner atoms are there? Only 7. Therefore, it is 7 by 8. Number of atoms. What is that? A, isn't it? So, we'll write 7 by 8 under A. B is at these fellows are B. Okay. Yeah. Face center. That means the contribution made by each face centered atom is half, right? We know that. Into 6 equal to 3. You have to watch my video on calculation of number of atoms per unit cell. Then you understand this better. Please do recall and then come back to these problems. Otherwise, you will find this difficult, right? Therefore, you have B3. What's the simple ratio? Isn't it 7 is to 24, my dear? Therefore, AB is the compound 7 and 24 for A and B respectively. Therefore, this is the right formula, A7B24. Where is the answer? It's D, right? Very good. Shall we move on to the next question? Yeah. The contribution of particle at the edge center to a particular unit cell is half, 1/4, 1 by 8. The question is again picked up from KSET. This time it is 2016 question paper. And what's the right answer? Yeah, before showing the right answer, let me draw a picture and then explain to you. You'll understand better. Okay. Now, I need to show the contribution of a particle at the edge center, right? Okay. Here we go. Look what I'm doing. Very simple. Just watch me doing this. Now join all this. It may not be a perfect geometry. Please excuse me for that. I'm trying my best with the tools available here. Okay, now join horizontally all these points. Now I think you're guessing something. Yes, you're right. Yeah, now observe. Yes, my dear. Can you see 4 cubes here? 2 towards us. That means facing us and 2 at the back. Just to differentiate, I can highlight. This is the top face of this cube. Back cube. Second. So you can take one more color. Should we take green? Yeah, see the third one, and fourth. Should we take red? Yeah. That means you're convinced that there are 4 cubes here. Okay. And we know every cube has 12 edges. Which is the edge that is, common to all the 4? Look here. Isn't this edge? I'm highlighting with blue once again. See, this edge is common for all the 4, right? Now, let us say at this center of this edge, I mean, we place a particle. This particle now is shared by 4 cubes, or you can say unit cells also, right? Okay, now 4 unit cells are sharing one particle, right? Simple mathematics. So 1 unit cell will get how much? Are you clear? One particle is shared by 4 unit cells equally. For 1 unit cell, how much? Simple. You have one, a roti. Okay, 4 friends have to eat equally. Then 4 of them have to share. So each person gets 1 by 4. Same thing, 1 into 1 by 4. Therefore, the answer is 1 by 4. Okay. This is the right option B. Are you clear? Very good. Shall we move on to the next question now? Right. The unit cell with the crystallographic dimensions A not equal to B not equal to C, alpha and gamma equal to 90 but beta not equal to 90 is what? Yeah, this is an obvious question. Definitely it depends on your memory, but I have given you a trick. Try to recall. This question is once again from KSET paper, that is 2015 here. Here is 2015 rather. Okay, and the options are triclinic, monoclinic, orthorhombic, tetragonal. If you don't remember or if you have forgotten the trick, then it becomes really difficult. So let me recall the trick once again for you so that it will be easy for us to go ahead now. I said, cub and tiger, right? Cub means cubic, tiger, T for trigonal. Then in that first set, I said A equal to B equal to C. Remember, but this A not equal to B not equal to C. The second set, they got an orange, so O for orthorhombic, remember? Then they gave the orange to a monkey, M for monoclinic. They asked it to try for triclinic. This is the second set, if you remember. I'm not reading the entire thing. Second set, in fact, this is the relationship between the edge lengths. All are not equal to each other, right? And in every first of the 3, that is the first category in that set, I said A equal to, sorry, it's not A, alpha equal to beta equal to gamma equal to 90. But here it is alpha, gamma. One more trick I said. Yeah, in the case of monoclinic, mono means 1, I said, draw 1 like this, then beta, remember. Therefore, it's actually alpha equal to gamma equal to 90, but beta not equal to 90. Therefore, the answer is actually monoclinic. Okay, so if you remember the trick, you can apply and it will be easy. Otherwise, it's completely memory based. Okay, that's why I gave the trick. Okay, now let's go to the next. But you do get questions on this particular topic. Okay, you have to remember all the 7 crystal systems, right? Okay, with that note, which primitive unit cell has, see once again, unequal edge lengths, A not equal to B not equal to C, and all axial angles different from 90. That means what? Okay, this is again taken from IIT 2019. Look at this. It's a recent question paper, right? And the options are tetragonal, hexagonal, monoclinic, triclinic. If you are not thorough with the concept, if you have forgotten the 7 crystals, which is really confusing, that's why I gave the trick. I'm again emphasizing that. But if you have not followed that or if you have forgotten it, when you look at all these 4 options, it will confuse you much more. Therefore, I request you to go through the concept and try to apply the trick properly. Then go and straight away tick the right answer without looking at the options. Okay, so let me teach you how you can do that. See, once again, just now I said no, A not equal to B not equal to C is the second set. Yeah, in that all are not equal. Which one? Axial angle. That means alpha not equal to beta not equal to gamma not equal to 90. This was triclinic. The trick was triclinic. Tri means I said 3. 3 means I said all 3 are not equal. Remember? Therefore, the answer is triclinic. And first of all, you should know this comes in the second set. A not equal to B not equal to, that is orthorhombic, monoclinic and triclinic. Okay, good. Shall we go to the next question now? Fine. The ratio of number of atoms present in a simple cubic, body-centered cubic and face-centered cubic structures are respectively. Once again, I don't want you to see all these ratios and get confused. Let's solve it and go to the right answer. This is once again from IIT JEE 2019, mind you. Yeah, two questions from the same chapter in the same year question paper, mind you. So this is very important. Okay, to make you understand this, let me draw once again so that you will enjoy, I feel. Okay, simple cube. First, let us draw. We have simple cube, body-centered cubic, and face-centered cubic, BCC and FCC. Okay, let's draw all the three quickly. So we have simple, BCC and FCC, isn't it? Let's join them now. Yeah, in simple, just try to recall. We have atoms only at the corners, right? In BCC, you have them at the corners as well as in the center of the body of the entire unit cell. And in FCC, as we know, they are at the corners as well as at the centers of every face. Okay, now let's take up the corner fellows. So you have corners. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, in BCC also you'll have all the 8, isn't it? Okay, good. In FCC also you'll have at the corners. Apart from this, we know this is primitive type, but these two are centered type of unit cells. So you have other positions. Here, body center. Very good. Here, we'll take one more color. Shall we take yellow? No, yellow we already taken. So we'll take red, okay? Fine. So here, face center. 1, 2, 3, 4, 5, and 6. Okay, my dear. So, number of atoms per unit cell now. Only at the corners. Contribution made by each corner atom is 1 by 8. So, how many such atoms are there? 1. Therefore, 1 by 8 into 8 is 1. If I have 1 here. What about here? 1 by 8 into 8 is 1 once again due to corner plus body center. The contribution made by the body centered atom is just 1. 1 into 1 is 1. Therefore, 1 plus 1 is 2. Here again due to corner. This I'm talking about corners. And this is body center. So corner 1, face center now. Face center is half, right? Each face center atom contributes half. So there are 6 now. Just now I showed all the 6 red fellows. So that makes 3, right? 3 atoms. Therefore 1 plus 3 is 4. So 1 is to 2 is to 4. So right option is B. Once you know this concept clearly, then it will be easy for you to tick the right answer. Otherwise, these numbers will actually bewilder you. So don't get into the trap. First, be thorough with the concept before you attempt any of the numericals. No numerical is difficult, okay? Provided you are thorough with the concept. Otherwise, every numerical, you will find it difficult when you are not thorough with the concept. This is my simple advice. Okay, my dear? In a face-centered cubic lattice, atoms A are at the corner points and B at the face-centered points. So, shall we draw quickly once again? It will be easy, right? Okay. So, we have a face-centered cubic lattice, right? Right? Just now I showed what is a face-centered fellow. Atoms at the corners as well as at the face centers, right? Good. Now, which atoms are present at the corners, my dear? A, right? A at the corner points and B at the face centers. This time B is missing. Okay. So, but A, all are present, right? Therefore, at 8 points. 1, 2, 3, 4, 5, 6, 7, 8 are there. B at the face center, but 1 is missing. That means there are 6 face centers. 1 is missing, means 6 minus 1 is 5. So let's take up one more color now. Take green. Okay, we'll choose top face, bottom face, the 2 side faces, and the front face. Okay. Somewhere here, let us say. Okay. Back face I have left out. So there are 5. Now tell me, A at the corner points. So simple calculation. Yeah. Contribution made by the corner fellow is 1 by 8. There are 8 such atoms, that is A. So it is 1. So if you have to take the ratio between A and B, A is 1 and B. Contribution is half, but there are only 5. Therefore, it is 5 by 2. So B is 5 by 2. Therefore, when you simplify this further, you get ratio as A2B5, isn't it? And that is the molecular formula. Okay. Where is A2B5? D, right? So the right option is D. And this is taken from IITJEE 2014 question paper. Okay. Yeah. Next question. In monoclinic unit cell, now this time they have specified the crystal system and they're asking you their relationships. This is much more tougher than the previous 2 questions, because here there are different relationships between the edge lengths and the axial angles or the face angles. So if you're not thorough, don't attempt this question. Okay. IITJEE 2014. See, I told you this type of questions are frequently asked. So you have to practice that trick once again. Okay. According to the trick, I said, yes, cubic and trigonal, carbon tiger. Yeah. In that, first one comes A equal to B equal to C. But this A not equal to B not equal to C. That means the second set. There's orthorhombic, monoclinic and triclinic. In that set, see, in all the options, the same thing you can find. Look at this to confuse you. So next, you should be very thorough with the relation between the face angles, right? This alpha, beta, gamma. Monoclinic. Again, small trick. Mono is 1, I told. Remember? Maybe a vague trick, but it's quite useful. 1, then make it like this for beta. Remove beta out. Then what is left out? Alpha and gamma. Both are equal to 90. Beta not equal to 90. Therefore, the right option is alpha equal to gamma equal to 90. But beta not equal to 90. Therefore, the option is C. Okay. Got it? Fine. Hope these questions have really helped you. If it is not enough, please practice some more questions so that you get a better grip. But we have tried to touch upon various concepts and different types of questions. But personally speaking, I would suggest you to practice many more such questions to get a better grip. Okay. Thanks for watching. Bye-bye.